Okay, so then we move on. Actually, our next presenter is also from AdGuard, and specifically his name is Maxim Topchu, and he is AdGuard's browser extension lead, team lead actually, and he's overseeing the extensions that are, well, protecting millions of users' privacy and security. And he has over 7 years of experience with deep expertise in browser extensions and related technologies. And I invite you to discover with me how AI can take ad blocking beyond filter lists, analyzing ads by their meaning and appearance. Maxime.
Hello, everyone. Thank you for coming. Today I want to talk about rethinking ad blocking with LLMs. Let me briefly introduce myself and what we'll cover. My name is Maxim. I have been at AdGuard for 7 years, leading the team that builds browser extensions and maintains the filter list infrastructure, from validation to distribution. Today I will talk about how ad blocking works, previous attempts at using machine learning for ad blocking, my own LLM experiments, and where this LLM approach is headed. I know you're probably curious about the LLM experiments, but first we need some context. To understand what LLMs can bring to ad blocking, we need to look at how ad blocking works today. I forgot switching slides. At the core of all ad blockers are filter lists, which are maintained by the community. These lists have thousands of rules that fall into 2 main categories: network rules and cosmetic rules. Network rules block requests to third-party ad service before content reaches your browser. It's fast and efficient. These rules can block, redirect, or modify requests. For example, the rule on the slide blocks evelads.com and its subdomains. But network rules can't block everything. Some ads are served from the same domain as the content, so blocking them at the network level would break the site. That's where cosmetic rules come in. They use CSS to hide unwanted elements directly on the page. For example, this rule on the slide hides elements with the class add_banner on example.com. When CSS isn't enough, like with ad injection scripts, we use scriptlets. These are small JavaScript snippets that blockers inject to counteract unwanted behavior. For example, this scriptlet stops scripts from accessing the alert function. Scriptlets have become filter developers' favorite tool because they solve problems CSS and network rules can't. So we have briefly seen how filter lists work. They are powerful for known patterns, but they have some limitations. They struggle with native advertising, require constant updates, and manifest with this made these updates harder. These limitations led to a fundamental question. What if we could eliminate filter lists entirely? What if the blocker could decide by itself what to block? No filters, no updates, no chasing ad networks. This is what users actually expect from ad blockers. This is what early machine learning experiments wanted to achieve as well. So with this motivation in mind, let's look at how companies and researchers tried to using machine learning to solve these problems. Project Moonshot from eyeo was presented at AFDS 2021. They trained a model on page structure using filter lists as labels. The model ran inside the extension to predict and hide ad elements. It worked, but faced challenges: imbalanced data, deployment difficulties, and constant retraining needs. Another machine learning project was presented by Brave Browser. At AFDS 2019, they introduced AdGraph. They built a graph tracking how everything on page connects, DOM, network, JavaScript, then classified resources based on context. AdGraph achieved high accuracy by tracing scripts back to ad servers, even with random names. But it required deep browser integration and constant maintenance. Brave also presented another ML approach called Percival, which focused on blocking ad images. They embedded a compact neural network directly in browser's render pipeline to classify images as they load. The results were impressive. They achieved 97% accuracy by analyzing image content directly. But it also had its limitations. It was vulnerable to adversarial images and only worked for image ads. Beyond industry efforts, academic researchers also joined the search for better solutions. One interesting project was AutoFR, which aimed to automatically generate filters. It generates URL patterns and CSS selectors, tests them, and learns from results while avoiding site breakage. Here results also were quite impressive. They achieved 86% effectiveness compared to EasyList, with rules generated in minutes. Another academic project was Sindbad. It focused on detecting when filter rules break websites. This project was valuable because site breakage is one of the main reasons why users leave ad blockers. It uses saliency, analyzing size, position, contrast to identify visually prominent elements like headlines and buttons, then tests them for breakage. Sindbad achieved high accuracy in detecting breakage with specific reports showing exactly what broke and which rules caused it. So we have seen all these experiments and research projects, but here's the thing. Despite all this work, none of these ML-based tools gained widespread adoption. So we can ask, why didn't machine learning replace filters? Well, there are several reasons. Filter lists set a high bar. Machine learning requires expensive data sets and ongoing maintenance. And building custom models from scratch is slow and expensive. And here arrive large language models and start changing the world. So maybe they can change ad blocking too? I'll explore how LLMs can be used for ad blocking in browser extensions. But first, let me quickly go through some key characteristics of LLMs. They appeared recently, but they are evolving fast. They are accessible via APIs. They come in both cloud-based and local versions. They are extremely capable. Also, they can be expensive. But what's most important for me is that LLMs allow us to test ideas very quickly. So let me finally show you my experiments with LLMs in browser extensions. First experiment is blocking by meaning. What was the idea? I wanted to block political posts on X that I didn't want to read. Traditional filters didn't allow me to do that. I wondered if LLMs could understand the topic and meaning of a post. To solve this, I decided to take the post content and send it to an LLM to ask if it's about politics. Since LLMs are a bit slow, I blur posts immediately, analyze them, and then unblur it if they are safe. And it worked. Semantic filtering based on meaning is possible. I prototyped this entire extension in just a few hours, something that would take months with traditional ML. Here I have a small demo, which is not loading. I don't know why. But okay, you could see there, post appears, blurs immediately. LLM analyzes and blurs if safe or stays hidden. Users can manually reveal blocked posts. But there was a problem. While I was experimenting on X, I noticed that some posts weren't being blocked because they were mostly images. This led me to the second experiment. Let's teach the blocker to see. Here you can see an example of such posts. Now it's on Facebook. This post is almost without no text, just an image. It's not only about the post without text. Even when text is present, websites hide it using obfuscated HTML. You can see it on slide. Here's a screenshot from developer tools of a Facebook post. You can see the sponsored label is hidden in randomized HTML. This is why we must stop analyzing the code and start analyzing what users actually see. So the idea was similar to the first experiment, but now we analyze what users see. Take a screenshot of the post, send it to vision-capable LLM, and ask it if it's about politics. It worked. AI integration took an hour, but taking screenshots by extensions was a nightmare. Let me explain why. One approach I tried was the debugger API. The debugger API allows to capture any element, even outside of viewport, but it causes page flickering, which can be annoying for users. The another approach I was using was Chrome tabs capture visible type API, the standard Chrome API for extension. This one has no flickering. However, it can capture on the currently visible elements in the viewport. And Chrome also limits how many screenshots you can take per second. So if you have multiple elements to analyze, you have to wait. Or you can only check, and also you can only check the elements that are visible on the screen. These experiments showed LLMs can analyze posts and decide whether to block them. Does this mean we can replace filter lists entirely? The answer is no. We still need them to know what to check. A web page has thousands of elements, and analyzing them would be slow, and analyzing all of them would be slow and expensive. If we still need to know which elements to check, the logical step is to connect LLMs with filter lists. Writing a new extension for every task is not scalable. We need something more generic solution. To create this generic solution, I took inspiration from AdGuard extended CSS library. Extended CSS is a JavaScript library that adds additional pseudo-classes to extend what's possible beyond native CSS. It has a contains pseudo-class that hides elements with specific text. I decided we could upgrade this approach to check semantic meaning instead of just keywords. This led to 3 prototypes: embedding, prompt, and vision. Let me start with contains meaning embedding. This rule uses embedding models which turn text into numbers that present meaning. We calculate the similarity between the element text and the criteria and decide whether they match each other or no. The advantage of this approach is that it's fast and cheap. We can cache it. The downside is that it needs threshold tuning and might struggle with multiple languages. Next is contains meaning prompt. These rules are using a simple prompt API where we just ask whether the content of some element matches the criteria or not. This is more accurate, requires no thresholds, and works across languages. The downside of this approach? Is it that it's slower and more expensive than embeddings? And the last one is contains meaning vision. It takes screenshots of selected elements and asks vision-capable LLMs whether the screenshot matches the criteria. After that, it works the same way as contains meaning prompt. The key advantage is that it can detect visual content that text-based method can't see. The downside is complex UX with potential flickering, as I told you before. So these three rules can provide filter authors with a flexible tool. They could choose embedding speed, prompt accuracy, or vision insight. Now that we have these three prototypes, the most important question arises. Are they practical? Can this actually work in production? To answer this, I analyzed the performance and cost for each approach. Let me start with embeddings. Initially, I started the extension with OpenAI's cloud model, and to be honest, the results were not great. But then I decided to try a small local model, and the results surprised me. It was faster, completely free, and achieved 100% accuracy on my tests. This shows that for certain tasks, some local models can actually outperform big cloud APIs. Next, let's look at prompts. Here the story is different. The cloud APIs performed best, with some achieving 100% accuracy in 1 second. Some took over 4 seconds, which is far too slow for a good user experience. And in this case, the local models just couldn't keep up with cloud accuracy. And finally, let's talk about vision. This is where things get really interesting. The accuracy is very high. Even local models perform well. Vision is often the most accurate method. Its key advantage is that it works on images, not text, catching ads that other methods miss. However, there is a major trade-off, latency. A 10 to 15 second delay is not practical for real-time blocking. Comparing all these methods, vision offers great accuracy, but with very high latency. Prompts provide a good balance of speed and accuracy, especially with cloud APIs. And local embeddings were a pleasant surprise, very fast and effective, but only for specific tasks. Each method has its strengths and weaknesses. What does this mean for the ad blocking future? In my opinion, vision is too slow for now. Embeddings aren't very practical for extensions to ship themselves, but they could work well as a built-in browser API. And local LLMs prompts are the most promising path for a real shippable experiment with Chrome Prompt API. There is also the challenge of user experience. The current approach with blurring elements isn't ideal. But with faster models, I think we could reduce this blur time. So what we have learned today. First, LLMs allow us to move beyond simple pattern matching and actually understand the meaning of web content. This opens up a completely new semantic approach to filtering. And second, LLMs give us rapid prototyping. Ideas that used to take months of engineering can now be tested in a matter of hours. While there are still practical challenges to solve, this new approach allows us to rethink what's possible in the world of content filtering. Thank you. I hope this has given you a new way to think about content filtering. The full source code is available on GitHub at the link shown on the slide, so feel free to try it yourself. It was great to present it today for you, so I'm happy to answer any questions.
Yeah, thank you for presentation. It's wonderful. Like it sounds similar that we do. So my question is, you pick up, like as I understand, like just correct me, because like you need to pick up some text or some block with a text or with image, then you make the screenshot of it, and then you send it to LLM.
Yeah.
Okay, so how do you see it should works from the user side? Because like I don't understand a little bit how it should work when user, for example, turn on ad blocker. So how do you see it? Like how it can be possible? Because you don't like send the whole page screenshot to LLM, but you send it as a part of it, and it's like mostly like a debugger thing.
No, actually, for my experiments, I have chosen Capture Visible tab API. It waits while the element appears fully on the page. After that, it makes screenshot of the whole page. I know that soon will be added some API for making just screenshots of some regions of the page, but it will be in the future. But as far as I know, in Firefox, it's already available. So after that, I am blurring this image and sending it to the LLM to analyze. When results returns, I'm unblurring the page, or it remains blurred. Depends on.
It requires like some LLM to work on the server side of your extension, as I understand, in this case. It can be local also.
It can be local, yeah. Also, Chrome local prompt. Chrome has its own prompt API. It supports Vision as well. Also, I have used some APIs for testing as well, so which are visually capable.
Okay, thank you.
Welcome.
It seems to me that one of the advantages of built-to-list is that you know before the request is made. And so with doing this, most of the time it seems like you would always have to make the request and analyze the content return, which is okay if what you're doing is you want to remove ads or political posts or something like that for distraction purposes or cosmetic purposes, but less so if you're worried about privacy or security or tracking or things like that. Do you envision there being a way that we would use this in content filters and be able to leverage this power for requests before the request is made, or fundamentally is it only kind of useful in that regard as a tool built to this developers?
I think it might be somehow used, but I selected some similar approach for my experiments, and I haven't thought about it can be sent before the page loads or something like that, because LLMs usually add overhead already, so page will load faster than LLM returns some answer. But I think it's one of the ways to improve the speed of this extension, of the user experience.
Actually, yeah, I had a very similar question to Devin. Do you think that one approach might be, by the way, first of all, fantastic results, really interesting to see. Thank you so much for presenting. I think it's really good to see some sort of practical research being done, as well as the Opus presentation earlier. Thank you. But yeah, to like analyze the request that's got outgoing and to ask the LLM, like a local LLM, something like, does this look like tracking data being set? Or does this look like obfuscated tracking data? Does it look like it's a tracking server that's being used? And providing some context from the page or something like that. Do you think that could work?
Yeah, I think it could work. You can provide to LLMs whatever you want and test whether it works or not.
On a practical level, is that possible? Is that easy enough to prototype?
I think yes. That's what I told, that LLMs give us ability to test faster, whichever approach you want. You can collect some data with this text. I just took some inner text from the element and send it and that's what I was sending. But I think you can add additional data and ask LLM to analyze.
Maybe this is just the same question as Depp's. Sorry if I eased it up. Yeah. Thanks. Thank you very much.
Thank you.
Don't be shy.
For a change, we have time. But okay, if there are no more questions, or if there are any others that come up later, we can venture into an early coffee break.